Let me start with this the first experiment on fractional quantum Hall effect. In fact, this probably should have been done earlier as we have began with fractional quantum Hall effect. But however, I wanted to introduce the formalism and the Laughlin states etc. Earlier. So, just to let you know that there are these three people who have written this physical review letters in 82, Sui, Stormer and Gossard. In fact, two of them got a Nobel Prize along with Bob Laughlin, whose picture appears below. So, this said that the abstract, it said that a quantized Hall plateau at h over e square multiplied by 3 is accompanied with a minimum in rho xx was observed at small temperature T less than 5 Kelvin in the magnetotransport of very high mobility two-dimensional electron gas when the lowest energy spin polarized Landau level is 1/3 filled. So, this was the first observation of fractionally quantized Hall plateaus. The formation of Wigner solid or charge density wave with triangular symmetry is suggested as possible explanation. Will not go into this last line in details, though we'll touch upon the nature of the quantum Hall fluid. This was as you see that there are three people on the right. This is Dan Sui, followed by in the middle Robert Laughlin, and then Stormer, who's on the left. And the citation said that for their discovery of a new form of quantum fluid with fractionally charged excitations, and this known to physicists as the fractional quantum Hall effect. Okay. So, going to the actual experimental data, you see the Hall plateaus. The Hall plateaus, these are showing some the quantization of the Hall plateaus, and they are seen at integer values 4, 3, 2, 1. And then there are other fractional feelings such as 2/3, half, 1/3 and 1/4, and you see that the temperature is low down to about less than half a Kelvin, which 0.48 Kelvin, and the corresponding magnetoresistitivities are being measured. Very importantly, these are high quality or rather high mobility samples. And the samples are sort of gallium arsenide and aluminium gallium arsenide, these heterojunctions. If you read that paper which I had shown, this physical review letters has information about the experimental details and the kind of samples being used. And this is the magnetic field is quoted in kilo Gauss, but it's about if you convert it into Tesla, it's about 22 Tesla that they have gone to. And the mobilities are of the order of 10 to the power 5 centimeters per volt second. So, these are very large mobility samples, and as you see that the temperature is also very low. The main thing is that these are cleaner samples with larger mobility, where the interaction effects become dominant as compared to the disorder effects, and that's what has created or rather given rise to these fractionally quantized plateaus. Okay. So, let me very quickly visit the lowest Landau level, and the properties will probably come back to it again. And mostly in literature it's written as LLL, and this is of course goes with a quantum number which we have discussed number of times, which represents the quantum number, the angular momentum quantum number, and this actually the unnormalized wave function that goes as z to the power m and exponential minus z square by 4 Lb square, where Lb is the magnetic length that we have talked about and z is x minus Iy. Okay. And so, these states are located within a radius which is given by Lb into root over 2m. Please keep in mind that this m is not mass, but it is the angular momentum quantum number, and the largest value of m that for which all the states will fall inside of a radius r is given by this m is equal to some r square, that's by 2 lb squared. So that's like the m max, the maximum value of m, and we have seen that, and we have sort of came to a conclusion that this really gives rise to a filling fraction which is 1 over m, and these m is equal to odd integers which are like 3, 5, 7, 9 and so on. Okay. And of course, the numerator here for the Laughlin states is equal to 1, but in practice we have seen other numerators as well, like as you saw that there are 2/3 and so on, there are 3/5 and so on, but these are by and large these properties of the lowest Landau level. We will come back to this again. We talk about the nature of the quantum Hall fluid. This Z is called as a Jastrow factor, and it tries to keep the electrons away, and it's multiplied by a Gaussian, which you see there is exponential minus z square by 4 lb square, which are the properties of the harmonic oscillator wave function. Okay. So there is something that we have seen. So let me sort of try to explain that why Laughlin states are good for understanding the fractional quantum Hall effect. How does it give rise to fractionally quantized plateaus and so on. And this is a slightly tricky explanation, so listen to me carefully. So we'll rerun the Corbino disk argument. And just to remind you that it is this is like a disk, okay, and so there is this and it encloses a sort of an opening in the middle through which a magnetic flux is thread by putting a magnetic field. This is where the electron gas stays, and the temperature is assumed to be low because we want the coherence of the wave function to stay. That is the electronic wave function has a particular amplitude and a phase. So the phase part is important, and it should be phase coherent. So this is the geometry that is called as a Corbino disk, and what happens is that which we have done earlier in the context of integer quantum Hall effect, that the magnetic field is ramped up, that is increased as the flux that is threading these geometry increases from 0 to phi 0 and then to 2 phi 0 and so on, where phi 0 just is equal to h over e, which are fundamental constants. Okay. So as it is ramped up from 0 to phi 0, and then what happens is that an electron is actually, so there is an electron that is transported from the inner edge to the outer edge, and the only conductivity or the resistivity that the system has is the Hall resistivity, and this Hall resistivity is seen to be quantized as h over e square, and there is a 1 over n there, and this n is an integer for the integer quantum Hall effect. And when we say that an electron is transferred from a sort of circumference to the outer one, when the phi 0 increases from phi 0 to 2 phi 0, that is the flux increases from phi 0 to 2 phi 0, then there are 2 electrons being transported from the inner circumference to the outer one and so on. So there are 1 electrons being transported, 2 electrons, 3 electrons and so on. So this Corbino disk according to Laughlin was seen as a quantum pump, okay, and this is how integer quantum Hall effect was nicely explained, though of course the argument that we talk about is depends on this radial geometry or these disk geometry. However, we could understand that this is really, the quantization is very nicely explained by this motion of electrons or the transport of electrons from the inner edge to the outer edge. Now, what happens when one has a fractionally quantized plateaus? Does it mean that E by 3 is transported? That is certainly not true, because electronic charge is known to be indivisible. Okay, so that cannot happen. So we have to understand it better. Okay, and this understanding can be achieved if we ask ourselves this question, that what happens to the Laughlin wave function as a flux quantum is threaded through the Corbino disk geometry. So, how does the Laughlin wave function or the Laughlin state changes? And so, if you remember, the coefficient of the Gaussian is in the Laughlin state, of the Gaussian is z to the power m. Z is the complex coordinate. Okay, so as the flux quantum changes, m goes to m plus 1. Okay, so this tells you that if m goes to m plus 1, then the maximum power of Zi, that is this Zi corresponds to individual electrons. The index I runs from 1 to n. So, the maximum power of Zi increases the m max from nm to nm plus 1. Okay. So, because quantum number m changes, so the total angular momentum quantum number, the m max would change from nm to nm plus 1. So, that tells you that if you need to incorporate it in the Laughlin wave function, then the new Laughlin wave function corresponding to this m plus 1 flux quanta is given by some this I equal to 1 to n. So, and then the Zi, and so this is the extra factor, and then it is a psi m, the old wave function, and then Z1, Z2 all the way till Zn. That is the wave function that we had for m quantum, m flux quantum. Okay. So, you need to take into account all these Zi's corresponding to all the electrons which run from 1 to n, in order to increase the total flux quantum from nm to nm plus 1. So, each one will contribute to this increase, and this was the earlier, this one on the right, psi m, is the earlier Laughlin state, and we have now this new factor which gives rise to this psi m plus 1. Now, quite arbitrarily, but it helps our discussion, we introduce some kind of origin of the coordinate system, some arbitrary origin of the coordinate system, say z0. This origin really does not make our discussion, any of the discussion, to be any weaker than I mean, the present discussion remains as it is. However, we introduce this in order to understand the electronic density, okay, the density of these corresponding to this Laughlin state, okay, the electronic density corresponding to the Laughlin state, and where would it peak and so on. So, this is an arbitrary origin. Okay. And if we include that, then of course we can write down this keeping this arbitrary origin as I to 1 to n, and now we do a z I minus a z 0, and again the same wave function that we have written down. Okay. So, it is quite important to see that. You see, there was a arbitrary origin being selected in the whole problem, which in the complex plane, which is like x0 minus I y0, and we are shifting all the coordinates of all the particles by that amount, which is zi minus z0, and there are a few conditions on z0. Let us see that. So, it is assumed that the single particle density remains uniform up to a distance LB relative to the edge of the disk. Okay. And we are talking about the wave function. So, basically the annular region of the wave function, or rather the radius of the wave function. So, now the probability of finding an electron at the origin is missing, such that the density within an area LB square about the origin is almost 0, or let us call it as significantly reduced. Okay. So, what I am trying to say is that the density is also uniform within a distance LB from the ring of radius r, which is obtained in terms of these LB into root over 2m, m being the magnetic quantum number. So, as m changes, these radii changes as a square root of m or square root of 2m, and so we have introduced an origin here z0, and the single particle densities, they remain uniform between LB and a distance LB from the edge of the ring. Okay. And that is how we are missing the electron density at the origin, rather it is shifted from the origin, or rather I mean it is shifted towards the edge of the disk. Now, this in standard notations of solid state physics, that is missing an electron is interpreted as hole. So, let me write that down. Okay. So, that means that we have a hole at the origin because the electron density is missing. So, what happens then? So, when the magnetic field is increased, m flux quanta are added to the system. So, because of that, m holes are created in the system. Okay. So, these are very subtle arguments, and they are very important for us to understand that how does the Laughlin state give rise to a fractionally quantized conductivity or the resistivity. So, once we have this, the resulting Laughlin state is given by, so that psi m plus 1 z 0, this is equal to product of I equal to 1 to n z I minus z 0 whole to the power m, and a psi m, this is, we have written it down earlier, and we wrote it again just to make sure that this becomes equal to, now this has a z I minus z 0. So, this becomes I equal to 1 to n plus 1 a z I minus z 0 whole to the power m, and you have a minus z I square divided by 4 LB square. Okay. So, these n plus 1, the plus 1 is coming because there is also a factor, similar factor in the psi m, which is old Laughlin state, before we have increased this flux. Okay. So, it tells you that the resulting Laughlin state, it sort of corresponds to n plus 1 electrons, and hence it has m into n plus 1 instead of mn flux quantum. Okay. So, this addition of an extra electron, okay, this extra electron that is being added, it compensates for the m added holes. So, added holes in the system, this is what we have said. So, this tells you the charge of each hole is let us call it as E h, which is charge of a hole, is minus E by m, okay, where m is the number of added holes in the system. So, now in this Corbino disk experiment, instead of an electron being pumped from the inner circumference to the outer circumference, so a hole which is equivalent to E over m electrons is pumped into the Corbino disk. So, let me write that. So, instead of an electron, I mean, we will just put this like one electron, what it means, there are a hole of charge E over m, we are talking about the magnitude, is pumped across the disk. Okay. That is, instead of one electron, there are these E by m charge that is pumped from, so this is a hole which has a charge which is E over m is pumped from the inner, from this A to B there. Okay. So, let us rerun the same argument that we have done for the Corbino disk. So, we have the flux is slowly increased from 0 to phi 0, and what we mean by slow is that we know that this T 0 should be much greater than 1 over omega b with h cross equal to 1, where omega b is equal to E b over m. Okay. So, this is the underlying assumption that you thread it slowly, so that the electronic wave function, it maintains a coherence, excepting the transport of one electron from the inner to the outer edge, nothing else happens. And this will give rise to an EMF, which is just from this standard electrodynamics. It says that it's a del phi del t, where phi is the flux change, and let's just take it as phi 0 to t 0. It is being changed from 0 to phi 0, so it's minus phi 0 by t 0, and this will induce a radial current which is equal to say n E h over t 0. Thus, this will give rise to a Hall resistivity. We'll call it rho xy or rho h, same as rho h. This is equal to E over I r, and this is like a phi 0 by t 0 and a t 0 by n E h, and this is equal to a minus h over E 1 by n E h. Now putting E h equal to minus E over m, so one gets a rho h to be equal to h over E square m by n. So the whole electron is transferred. Whole electron means one electron. One electron is transferred when the flux increases not by just phi 0, but by m phi 0 units. Okay. So, this is the assumption that, or rather this is how we reconcile this the fractionally quantized Hall plateaus. Okay. So, this really even the quantum Hall pump thought experiment really explains these fractionally quantized plateaus, and the way we go in order to explain has been just laid down in front of you. Okay. Let me do now the nature of the quantum Hall fluid. And will give you an analogy to plasma. And the analogy is only just to say that there are these charge neutral system, and there are some charges and there will be a background charge in order to compensate for it. But plasma is usually at very large temperatures when this ionization of the gases occur. However, we are talking about a very low temperature. So, in a way this is not the classical plasma that we are aware of, but it has some similarities, which is what makes this the quantum Hall fluid very interesting. And this analogy makes us understand the system or these fluid better, that there is indeed there is a background which neutralizes the charge. Okay. So, just to understand that, let us write down the Laughlin state once again. This is that j less than k, and then it is going from j 1 to n. Well, I believe this is clear. So, it is actually j from 1 to n, but then j is less than k such that at zj minus a zk whole to the power m exponential minus zi square by 4 lb square, and m is the quantum number, and so this is I equal to 1 to n, and this lb is the magnetic length that we have talked about several times. And this tells you that this is a factor which tries to keep the electrons away, and if one electron tries to come on top of another electron, there will be the wave function will vanish, and this is related to the exclusion principle. These are fermionic wave functions, and importantly this corresponds to a filling which is equal to 1 over m, where m is equal to 3, 5, 7 and so on so forth. Okay. These are all known to us, and even though many other fractions are found, as I told in experiments, we still rely a lot on the Laughlin states in order to understand the nature of the quantum Hall fluid. Okay. And very importantly, this is, if you change the Zj to Zk or back, I mean, then you pick up a negative sign and so on. So what it means is that your psi m, so I have a Z1, Zi, Zj, Zn. Okay. So this is equal to minus of this Z1, Zj, Zi, Zn. Okay. This is what it means. So this is antisymmetric, and there is a property of the fermionic wave function. So if you do this, it picks up an antisymmetric property. So bosons are symmetric. So if you do that for bosons, they don't pick up any sign, and that's the reason that they are written as a determinant, called as a Slater determinant, and so on. There is another very interesting thing, and which has got relevance to our present discussion. If we try to calculate the density, okay, that is the probability density, which in a quantum mechanical sense is given by the psi m square. So this is equal to a psi m z mod square, and this is equal to, we'll take, so this is like a product j less than k m z j minus z k whole to the power m exponential minus I equal to 1 to n and a z I square by 4 L b square. It is this and then mod square of that. I just wrote down the entire thing once again and then take a mod square of that. Okay. Very interestingly, these two terms, they behave completely differently if we are talking about the density of the quantum Hall fluid. Okay. So this is called as a Jastrow factor. Let's just name them as a Jastrow factor, and let's call them as a Gaussian. Okay. So Jastrow and Gaussian. So the Jastrow of course keeps the fermions away, and this Gaussian term actually shrinks as the fermions spread out. Okay. So one grows as the fermions spread out, or they are at larger distances, and the other actually shrinks, or rather it falls off quickly as the fermions are they are at larger distances. So this is Z I square. Okay. So in this competing scenario, how does one ensure uniform density? Okay. And so this is a very important thing, that because the uniform density, if it is not there, if there is a variation in density, then there are different problems that from one region of the fluid to another, then of course that means a quite complicated thing in any sort of way, that this is quite complicated, and on top of that such a sort of product of two terms in the wave function, they give competing sort of behavior. So this is where the plasma comes. Okay, the analogy to the plasma which we have just said, that comes, and let me write down this. So let's write down this density, let's call it just a Z, just to and without any prefactor or anything, let us write it as V plasma, where V plasma is this potential of a plasma, and beta is, in the conventional sense, it's equal to the 1 over T or 1 over kT. That's the inverse of temperature that we are aware of. So, this is how we write down the density of the Laughlin states, and now we will extract out the information of each one of the terms and maybe call them as V1 and V2 or V plasma 1 and plasma 2 and so on and so forth. So, if we do that, then the V plasma actually comes out, which is coming from these Jastrow and the Gaussian, it is equal to 2m square j less than k log of z j minus zk and plus m by 2 lb square sum over j, for example, and zj mod square. So, sometimes we are writing it j, sometimes we are writing it I, but it means the same thing. We are trying to label the electrons, the individual electrons. So, this actually coming from the Jastrow factor and this coming from the Gaussian. Okay. Now, if you remember that this is actually the potential in 2D sort of, suppose you take a line charge or then the potential at a distance on line charge, that comes as a log of this, and this term is a mod the coordinate square. So, this is log of the coordinate and a mod of the coordinate square. So, these are the two terms. One can easily identify that beta is equal to 1 over m. So, that the temperature is not a real temperature, and just to remind you that plasma really, the classical plasma occurs at very large temperature, whereas here we are talking about very low temperature. We have shown the fractional quantum Hall experiments were being held at down to less than half a Kelvin, okay, that's 0.48 Kelvin and so on. So, ideally about 2-3 Kelvin or 4 Kelvin and so on. So, the analogy to the plasma, as I said, that it is because of this making there are classical plasma constitutes of particles that are with charge m and with a uniform, that is a neutral background, and then so sort of the existence at, of course, at a very low temperature plasma like state is counterintuitive, but here because it sort of will show that it looks like that of a plasma, there is a new state of matter, so to say, and it is called as a Laughlin state, often referred to as a Laughlin state. Okay. So, let us try to understand the V plasma, that is the potential due to the plasma. Okay. So, if you remember that the electric field and the potential, they are really related by these these are the charge for a point charge, they are like QR by R square, and a phi of R is equal to minus Q log R. That is the form of the electric field, and this electric field obeys an equation which we know that is called as the Laplace's equation or the Poisson's equation, which are like 2 pi q delta 2 r. We are talking about in 2 dimension, and delta 2 is nothing but the 2-dimensional Dirac delta function. Okay. So, so the first term, the Jastrow term, so let us call it as a V1, let us call it as a 1 and a 2. So, the V plasma 1 term, this is like a m square, probably we are missing a factor, we will adjust that, j less than k and a minus log of zj minus a zk, that is your. So, this is the first term, and as I said that we missed a factor of 2 here, which one can actually absorb it in the definition of beta. So, instead of beta equal to 1 over m, it can be actually 2 over m. Okay. So, this is how one can take care of it. So, this is one term, and the second term can be understood if we see that if we take a del square of a term such as z square by 4 equal to 1 over LB square, Okay. So, this is that the del square phi equal to the 2 pi this thing that we have written down here. So, this 2 pi q delta square r. So, this is equal to nothing but this will give you a rho, which is the density in comparison with this term. So, this density, which is written as a q, this is the density part. This is the density which for a point charge is written as q into a delta function, because we are in 2 dimension, we have written it as delta 2 r. The density is written as minus 1 over 2 pi L b square. That tells you that the V plasma 2 this is equal to a z square by 4. Okay. Those are the 2 terms corresponding to the quantum Hall fluid, which we are trying to visualize as a plasma. So, this term this denotes the energy of m charges interacting with the negative charge density. So, this also tells you that there is an area of 2 pi L b square. So, this is an area of this, it contains 1 flux quantum. Namely phi 0, which we know is equal to h over E. Okay. So, this makes the background charge density, which is there for making it charge neutral, the background charge density is B over phi naught, which you know that it is equal to density of flux in unit of flux quantum. So, this is this charge density, which is same as the density of flux in the unit of flux quantum. Of course, this when you multiply B by A, the area which is here 2 pi L b square, it gives you a total phi by phi 0. This is the flux density per unit area. Okay. So, the last question that we have is that this Laughlin wave function explains a lot of things about fractional quantum Hall effect. So, one needs to understand it very well, one needs to understand its properties and so on. So, there are many ideas that have been simply thrown down, and in order to explain a lot of things that are important in the context, such as understanding the quantization of the plateaus to be not at integer values but at fractional values. Then they have to have this basic property of not allowing 2 electrons to sit one top of another. They have to have this property of the harmonic oscillators, the Gaussian of the harmonic oscillator. This is quite important because the energy levels really come out as n plus half h cross omega. Okay. N denotes the quantum number corresponding to the energy, and m which is the quantum number corresponding to the z component of the angular momentum, that gives us the degeneracy. And we have seen that it can, running through a sort of familiar this Corbino disk argument, we have shown that one sort of electron is transferred when not one flux quantum, rather m flux quantum moves from the inner edge to the outer edge, and that would give rise to plateaus at fractional values where m is an odd integer. We are excluding 1 for obvious reasons. I mean, the plateaus are seen at if m is 1, then of course it does not give you a fraction which is with an odd denominator. All these things, they are being nicely explained. And if you want to ask this question that how good are they, and then numerical work being done. So let me write down the question: how good are the Laughlin states? Okay. So people have done numerical calculation on few particles, okay, on a number of potential which include 1 over r, which include minus log r, which include exponential minus is r square by 2 and so on, and they have found more than 99% overlap with the ground state energy, which means that the Laughlin state is very robust, very correct and so on. And remember that he wrote it down based on symmetry arguments, based on really the understanding of the problem without having to solve very complicated equations, Schrodinger equations and many particle equations and so on. So it is indeed a very good approximation to the actual state because of this, the numerical values have confirmed So we just write almost perfect overlap. Okay, so we are almost nearing the discussion to the completion of this fractional quantum Hall effect. We'll do one more thing to end this discussion on this not only fractional quantum Hall effect, but also the course on quantum Hall effects. Let me give you a half a minute explanation that why is this quantum Hall effects. In fact, it should be just quantum Hall effect, but however there are these spin Hall effect and etc., and then there are these anomalous Hall effect, quantum Hall effect, which is without really requiring to have an external magnetic field. That's why, and then discussion actually continues, and that's why this S has come into the picture. But I hope the idea is clear. These are really things that one should read a lot of literature in order to have a good understanding of what is happening, why are there fractionally quantized plateaus. Once you understand that there are very nice explanations of integer quantum Hall effect, that is plateaus occurring at h by ne square where n is an integer, then going over to this n not being an integer and it's a fraction, that requires one to understand that really the interaction between the electrons, which is a many body interaction that we are talking about. It's not just, it's a pairwise interaction of course between two electrons taking place, but in the bath of many particles. Okay, so these two particles are interacting and each particle is interacting with another particle, and taking into account this, trying to solve some equations would have been only a task that can be done by very large and powerful computers, which is what we are showing you, that for a few particles taking wave functions, or rather these potentials to have different forms, the Landau states or the Laughlin states are being confirmed to have a very good overlap with what's going on in the system. And so it is the nature of the state is that of a plasma, say a quantum plasma, which occurs at very low temperature. So there are these charges that are moving around, and these charges are in a background of other kind of or other sign of charges, so that there's a overall charge neutrality that exists in the system, and this is what has been discussed so far.